with good topology means compact, simply connected, without boundaries. According to Poincaré, such a manifold, three-dimensional, smooth, compact, without boundary and simply connected, should be homeomorphic, diffeomorphic actually, to three-dimensional sphere. And that was open almost 105 years, that conjecture, until Hamilton tried but failed. It was a Russian mathematician, Kellerman, with the tools of Hamilton. He was successful in settling the Poincaré conjecture.
So, what's an example of a smooth manifold simply connected without boundary?
Smooth manifold is a topological manifold on which a smooth...
simply connected without boundary.
Yes. Without boundaries, it does not have a boundary. For example, a closed ball.
It has a boundary.
It has a boundary. Right? So it's without boundary. And simply connected, roughly speaking, if we have a rubber band, we can expand or shrink it without leaving that surface. That's simply connected.
Excuse me, Professor Deshmukh. Without boundary, I think any set without boundary, you cannot, for example, study any problem on this set.
Why? I don't think so.
All
you
study. And the initial conditions also.
The problem is we have the habit of looking at plane or space, Euclidean space. No. Sphere, for example, is without boundary. And you have ample, even partial differential equations for the sphere. Then similarly, you have
Or a cube.
yes, a cube, the cover, the box in which you bring your computer. That is a manifold without boundary. Right? Well, see, what happens is we have habit of thinking in R2 or R3. R2 especially. Yes. All right. So, this was Poincaré conjecture. Now, what Hamilton tried was the following. Being compact, very nice topology, it is paracompact, and therefore such a manifold always has a Riemann metric. Always admits Riemann metric. So now, this is that manifold, but because this metric, you don't know, it may have some draws as well as some wells. These are positive, strictly positive curvatures, these are negative curvatures. Could be some deep wells as well as some crests and troughs, some high positive. So that was the problem in front of Hamilton. In order for that to be diffeomorphic to S3, because S3 has uniform distribution of curvature. Diffeomorphism allows even ellipsoid is a diffeomorphic object. For example, S2. An ellipsoid is a diffeomorphic to S2. So diffeomorphism does allow for smoothing these hills as well as wells. But sometimes there are strong obstructions. These obstructions are removed because of the nice topology. So what Hamilton realized, there were hundreds of attempts to settle Poincaré conjecture. People came through algebraic topology, people came through differential topology, all of them failed. Then Hamilton realized that there is something called heat equation. Heat equation has the property that the potential is distributed uniformly on the dome. The temperature is distributed uniformly. So with that idea, he developed the following. This metric is allowed to be deformed. And this is a symmetric tensor. Metric is a symmetric tensor. He realized that there is automatically inherent symmetric tensor on a Riemannian manifold that is called a Ricci tensor. He asked for the solution of this heat equation. Where this Ricci is the Ricci with respect to the evolving metric. So the metric is per term, and you get an evolving metric. He asked that metric satisfies this differential equation. This is actually heat equation. And he called it Ricci flow. And he attempted to solve this differential equation under the initial condition, that at 0 times 0, the original metric is attained. His first attempt was to solve this equation using diffeomorphisms of M. He pulled back the metric and then multiplied it by some scaling factor, and that was his evolving metric. He tried this as a solution of this. And the solution, the stationary solution of this Ricci flow gives what is called as the Ricci soliton. That is, on that Riemannian manifold, there exists a smooth vector field. What are these? These phi t's are diffeomorphisms. It turns out that trying this type of solution gives a vector field such that these phi t's are flow, is a global flow of this vector field xi. And then, in order that this is a solution of this Ricci flow, this is a solution of Ricci flow, it turns out that you need reach that this vector field satisfies the following. Lie derivative of the metric with respect to xi plus Ricci of this metric should be proportional to the metric. Lambda is a constant. And this is how Hamilton reached what is called as a Ricci soliton. So the answer, question, what is the Ricci soliton? This is the answer. It is a solution of the Ricci flow. This lambda is a constant. A Ricci soliton is called expanding, stable, or shrinking. According as if it is less than 0, it is expanding. stable if lambda is 0 and shrinking if lambda is positive respectively. So, as I said, Hamilton, though he reached to ricci soliton, was unable to settle Poincare conjecture. Then, this German mathematician, Bellarmine, he, using tools of Hamilton, proved that the Poincare conjecture is true. That every such manifold is diffeomorphic to S3. What was the... Now, before I tell how Poincare proceeded, let me define one more thing. This xi coming in ricci soliton is called potential field. Could have what? The troughs as well as crests for curvature, right? Now, if lambda is strictly less than 0, what happens is this is unable to be removed. The manifold ultimately goes towards negative curvature direction. Stable, flat-like, and shrinking means where these whales are blown out, and this is also smoothened so that all the surface becomes flat, right? That okay? All right. Now, yes, this is called the potential field of the slot. Now, it is possible if this potential function is a gradient of a smooth function. Then this ricci soliton is called a gradient ricci soliton. There are many examples, especially on non-compact cases. Yet here the compact geometry, the compactness is not used till we reached the solution. This does not require the compactness. It is in the proof of Poincare conjecture all these niceties of topology are required, right? This holds even for non-compact manifolds. So if the ricci, this potential vector field is a gradient of a function, then it is called. Now, what Bellarmine, his first breakthrough was the following. Compact, of course, all objects are without boundary. So I will not mention without boundary. Compact ricci soliton is gradient. It was his first breakthrough, Bellarmine. The compactness forces that the potential vector field should be a gradient. That has to be gradient. And then the simply connectedness was utilized. And then the rest of the part was not very difficult. What was very difficult was showing that the compactness forces the vector field to be a gradient of a smooth function. So this was the story of Poincare conjecture. So now it is settled. This Poincare conjecture is over.
Can you write his name, please? What's his name?
Bellarmine.
Yes.
A very proud Russian mathematician who refused even to accept Fields' method he was offered. All right, so it is finished. The Poincare conjecture is finished. Then after that, what about geometry of Ricci, soliton, post settlement of Poincare conjecture? It turned out that such a beautiful object it is. It goes with application in economics, in medical fields, especially brain surgeries, statistics, probability, economics, to the extent of the transportation problem, and it has spread, right? But I am a geometer, so my interest is what is next post Poincare conjecture on the geometry of Ricci soliton. The next question is the following. You know, there is what is called as the trivial. What is a trivial Ricci soliton? If this potential field is such that its Lie derivative of metric with respect to it is zero, what it means is the flow of exile consists of isometries. That is the meaning of that. If this is zero, then the Ricci soliton is called a trivial Ricci soliton. So what does triviality mean? This is gone. Ricci is proportional to lambda g. What happens for a Ricci soliton? Ricci. And such spaces are called Einstein manifolds, where this lambda is called Einstein constant. So the next question on geometry of Ricci soliton, post settlement of Poincare conjecture, was to find conditions under which a Ricci soliton is a trivial Ricci soliton. Recently, lot of attempts are there in this direction. As I said, apart from application of Ricci soliton, different areas in humanities and other scientific areas. So recently, but before that, let me also introduce one thing before we give. I give what we have recently proved. On any Riemannian manifold, there is a Laplacian operator, Laplace operator, defined on ring of smooth functions. And this is defined as divergence of gradient. Laplacian operator, right? Especially if the manifold is compact, the eigenvalues of Laplacian One of the eigenvalues is of course 0 because constant functions, right? Because of constant functions. Eigenspaces are. Then you have this sequence of eigenvalues. This is called the first non-zero eigenvalue. And there is an eigenfunction. There could be several which satisfies this. Negative sign is used because of electricity of the Laplacian operator. There are people who define this as negative, so for them it is a Laplacian operator. F is lambda 1 times F. I will use, for example, the sphere with canonical metric. The first eigenvalue is n. This is an example. All model spaces, first eigenvalues are known, like projective space, complex projective space, and all good spaces, their first eigenvalues are well known. Now, what we have proved is the following. This is our humble contribution to this problem. An n-dimensional compact shrinking of positive Ricci curvature. So we start with a shrinking compact Ricci soliton of positive Ricci curvature. It's trivial. If and only if its scalar curvature is satisfied differential inequality. This is a characterization. This thing gives a necessary and sufficient condition for a compact positive Ricci curvature, compact Ricci soliton is trivial if it satisfies the Ricci scalar curvature satisfied. What is a scalar curvature? Scalar curvature is the trace of Ricci. It is a smooth function. This is the result we have achieved. Of course, still it is pending publication. Idea of proof. It's a long proof. He just sketched the idea of the proof. Sketch of the proof. First thing is this, that ricci soliton, compact, implies for some smooth function. This is the Kellerman's result. Every compact ricci soliton is gradient. Then the second, with these conditions, then the second thing is that a ricci operator operating on xi turns out to be let me call it F. This is the second value.
Lambda 1 minus lambda or lambda minus lambda?
Lambda 1 minus lambda.
What is lambda 1?
I think call that. Because lambda, in general, lambda is greater than lambda. So this term is negative.
No.
In the case of a
No.
trivial...
Those are excluded here. Here only those manifolds are included for which the first eigenvalue is, look, for trivial example, for example, there is no example compact where lambda 1, the first eigenvalue is smaller than the phase constant lambda. For example, in sphere, what is happening? Lambda 1 is, look at the sphere. Canonical metric. There is a gradient vector. And this is n. Why? This is, what is ricci? Right?
Yes.
So that is n minus. Whereas what is lambda 1? Right? And all known compact spaces have this property.
Yes.
Of course, there are examples.
No compact.
Yes, non-compact. But those are not shrinking. Sometimes what happens?
Because TD and
Yes,
expanding
there are expanding mostly of them.
must
So
be,
still
trivial,
positive.
trivial,
Yes.
yeah.
So the second finding, because of gradient ricci soliton, it happens. Third ingredient in the proof, we proved that should be half now I have to I should not rely too much on the memory. Let me go to the proof. Yes. Yeah, that's correct. Also, fourth ingredient is the maximal principle from analysis. What is that? If we find out divergence of this, it turns out to be n lambda minus s. And as a consequence, what happens is And then maximal principle tells you the gradient of this. Gradient of this norm, gradient of this is minus grad s, but I am taking norm is always greater than first eigenvalue this is the maximal principle on the even it is available in non-compact spaces. Only what is required there is the function should have compact support. This well known, and actually it is this property, this this is known as the maximal principle. And this how then in analysis they define lambda 1 to be infimum of all functions such that and infimum of what? Infimum of this integral m norm grad f square or integral m norm f square. Infimum of this is called, where these functions run over what? Zero integral functions, right? Integral of f is zero. This is called maximum principle in analysis. So using that, we have this. Because the manifold is compact, integration is available. This is the fourth ingredient in the proof. Also, there is what is called as the Bochner inequality. That holds for all smooth functions. Now, Bochner identity. For any smooth function, this holds. Where this is the Hessian. And we apply it for ricci scalar curvature, so I will have this. That holds for any for smooth function on the manifold. So you have the Bochner identity. Then what happens is we compute because Ricci's tensor linear in both slots. What you have is and it is symmetric moreover, minus 4 lambda plus 4 lambda squared Now from here, we get, on taking inner product with gradient S, I will replace this term by that. And the last part of it. we integrate this. We have Bochner identity giving this thing equal to minus norm A square integral. And then we have this by minimal principle related to this on integration. And, here, appreciate the anxiety. And here we have already obtained this. So all the quantities on that side are estimated by integrals. And therefore, the final situation we reach at this. We are replacing this by a smaller quantity, but because of this negative and the shrinking means this is positive. So if I am going to replace that with that, I will find that inequality. And putting all these things together with small manipulations, we reach to the following. I will write down the final thing. Minus, because this goes on that side. Plus. Yes, to enlighten that. And that thing square, that is n lambda minus s. So final estimate is this. Now, under our assumption, this thing is negative. This is symmetric operator, Hessian operator. And the Schwarz inequality tells us that one by n, trace of Hessian is Laplace. This is the Schwarz inequality. So negative of this positive is negative. Non-positive, this is non-positive, this is non-positive. Whereas assumption on the Shih curvature is that positive. So what you got is positive integrand is less than or equal to non-positive thing. So both of them are zero, and ultimately that gives us, because the Ricci curvature is positive, this vector must be zero. We achieve this as well as we achieve as well as equality holds there. So we have these equalities. And these are ingredients in proving that with a little effort, then it turns out that Ricci equal to lambda g. And this proves that the Ricci soliton is trivial. And the converse is trivial. Why it is trivial converse? Conversely, suppose Ricci soliton is trivial. Then you have this. So this gives S equal to n lambda and scalar curvature constant. So this is arithmetically satisfied. This side will be 0, this side will be 0. So it is satisfied. The converse is true. There are other results, but today I picked up only one result for this lecture. And here I will wind up because I have lecture after this, and I brought the attendance sheet also with me.
Thank you. There are questions, please.
Maybe Dr. Goy, Professor Goy, and Hoderi, these are the people who are in this area, so they may have some comments. This result is yet to be published. It is under process.
So when the ricci soliton is trivial, we say that it's Einstein manifold?
Not every Einstein manifold is. Not every Einstein manifold is trivial ricci soliton, but if ricci soliton is Einstein, it is trivial, it is Einstein.
And this includes any compact, shrinking ricci soliton with scalar curvature, constant scalar curvature.
Yes,
Yeah.
yes,
Yeah.
yes.
Include.
Yes, it is included there.
And this...
This is most active area. Thousands of people are working in the ricci geometry of ricci soliton. Yes.
And this differential inequality, is it
Yes.
always easy to verify if it's holds or not?
Yes, yes. It's very
Given
Yes.
ricci soliton?
Yes, but sometimes it's very hard to find Laplacian of scalar curvature. Hard, because scalar curvature itself is a second order differential equation itself, because a trace of Ricci is a trace of Riemann curvature, and it involves second order derivative terms. So that's the, if it's constant, very easy. But like in Euclidean spaces, it's zero. So, and there are some good spaces in which scalar curvature has nice expression. Then yes, it's possible. One last note: the competition has increased, and therefore, unless there is hybridization, unless you bring tools from different areas. For example, in ricci soliton, from where they brought the tools? PDE, partial differential equations, as well as analysis. Unless we use tools from different areas, no good research is possible. I mean, of course it is possible, but it makes very interesting if many areas interact together. For example, if you look at Hessian operator theory is involved, maximal principle from analysis is involved, and the Stokes theory is involved. Stokes theorem is global analysis, actually. Their own theory.
Have you published anything?
Sorry?
You haven't published this yet.
This is under publication. This we sent to a journal. We are waiting for the answer. Yeah. Actually, I took a copy from the journal submission. That's why you will find your numbers. Yeah.